discuss a lot in class. So when do we use energy? When do we use forces? A good time to use energy is when the force applied is not constant. So in our example here, we have a spring that's compressed, and we're going to shoot a ball up, and we're trying to figure out its maximum height. So since the force is constantly changing while the spring is decompressing, and that's because, remember, a force of a spring does equal minus kx. And the negative sign there just means is the force is always opposite to what the x is. So x is pushing down, going downwards. Our force is now positive, going against it. That's what the purpose of the negative there is. So the best way to do this is by energy. So in this one, we're just going to have elastic potential energy. That goes to gravitational potential energy. Much easier way of doing it than dealing with all the different forces there. So we just have one half kx squared, of course. Is equal to mgh. Okay. Now we have to remind ourselves for a moment. So there is a formula that says work, conservative minus work non-conservative. It does go to change in kinetic energy here, of course. So let's talk about our work of the spring, for instance. So we're not going to have any friction force in this, so there will be no work non-conservative. So the spring, in this case, is giving positive work to this. So we should see a positive kinetic energy change, right? So whenever work is positive for the object, its velocity is going to go up. When it leaves the spring, though, we have largely a conversion into gravitational potential. So the kinetic energy is dropping. So from the perspective of the ball going upwards, the work conservative is pretty much positive as we're going here. We're losing a little bit of gravitational, but not much. But once it leaves the ball going upwards, the work now conservative is negative with respect to the ball. Why? Because the velocity of the object is getting smaller. Okay, but we're not really losing that. That's going into gravitational potential energy. Okay, so from the perspective of the ball on the way up, the work conservative is negative because its velocity is changing, getting smaller. But just remember that that's being stored into gravitational potential. On the way back down, and we know it'll fall back down, now the work conservative is positive for the ball because now its kinetic energy is changing, but the gravitational potential energy is losing it. Okay, so on the way up, we say the work is being done to the gravity field as potential energy rises. On the way down, the work is being done to the ball as its velocity increases and the gravitational potential energy is getting smaller. Now, one more quick example. Let's say we have an object that is traveling with a velocity v here. Okay, and we do have a coefficient of friction here. Now, let's say I want to find that coefficient of friction. This is a good example. So we just simply watch this thing. It slides to a stop in a distance d. Okay, so in this case, it's just a kinetic energy conversion into thermal energy. There's no applied force on it. We're not going up or down. It's just a real quick kinetic energy. We're losing it into thermal energy here. So I'm just going to do 1/2 mv squared equals mg mu, okay, times d. Why would that be so? Well, this object is moving. We just have force friction going against it. There's no applied force. And of course, we have normal and gravity opposing each other. I'm not going to label those. We know those by now. Okay, so let's get back to our equation. So work conservative plus work non-conservative goes into change in kinetic energy. Okay, now sometimes I put a minus here, okay, because our work non-conservative is always going to be negative. So sometimes I put a plus, sometimes I put a minus. In this case, I put a plus. But I always remember that our work non-conservative is always negative because that leaves the system. So in this case, our work non-conservative is thermal energy, and there's no work conservative. There's no force applied in this situation. So we know that this is negative, therefore kinetic energy is going to be negative. Okay, so that's just another way of looking at it with the work kinetic energy theorem.